under session 5. So we're going to talk about the fault friction implementation and run through some examples. So the concepts we'll cover in this session are spontaneous fault rupture. That's what we call when we have the fault friction. We'll do both quasi-static and dynamic simulation, and we'll look at static friction, linear slip weakening, as well as Dietrich-Arena rate and state friction with the aging law. And as part of this, we'll be, in addition to just the friction itself, we'll discuss the nonlinear solver parameters, the absorbing boundaries and dynamic simulations. We'll make use of time-dependent Dirichlet boundary conditions and initial and time-dependent fault friction perturbations to nucleate the rupture. So recall from our introduction to Pilot on Monday that we talked about the fault tractions coupling deformation across the interface. And so we looked at these equations where we had the Neumann boundary condition in a similar form to the internal tractions that have the opposite signs. On the positive side of the fault face, we have negative times the Lagrange multiplier. On the positive side of the fault face, or on the negative side of the fault face, we have positive times the Lagrange multiplier. And we also have the constraint equation written here in terms of the slip and the relative displacement integrated over the fault surface equaling 0. And again, we wrote both the Lagrange multipliers and the slip in terms of basis functions, a linear combination of the basis functions, sorry. And we have a Lagrange multiplier traction terms and our constraint equation. Now, when we look at the fault constitutive model, our constraint is that the Lagrange multiplier for shear has to be less than or equal to the traction from the fault constitutive model. And in Pilot, we use the form here for our shear traction associated with friction. So if we're in the compressive regime, that is, we have compressive axial tractions on the fault, then the friction is a function of cohesion minus the coefficient of friction times the normal traction. So the normal traction compressive is negative, so this right-hand term is positive, giving us a positive shear traction. When we have the fault normal is equal to 0, we have cohesion. And when the fault opens or is under tension, then the friction is equal to 0. So that's this bottom piece so within the fault constitutive model, if the traction is greater than, if the normal traction is greater than 0, we end up with this bottom case. But then when we enforce the actual boundary conditions, we're using this bottom equation 9, where the product of the normal traction and the normal displacement is always equal to 0. So if we're in compression, we have no interpenetration or opening. So then if T normal is less than or equal to 0, then U normal must be equal to 0. If T normal is greater than 0, then U normal is equal to 0. I'm sorry. If T normal is equal to 0, then U normal is greater than 0. So that allows us to handle the fault opening. So when the fault opens, the fault becomes a free surface. In solving for friction, we have a nonlinear problem, as we discussed yesterday. So the way we do this is we first perform a nonlinear iteration, and this is assuming no additional slip. And so our slip is basically, we're assuming the fault is locked at that time step. And we check to see if the fault constitutive model is satisfied. If it is satisfied, then we're done in terms of the fault constitutive parameters. We don't need to make any changes to the solution. If it is not satisfied, then what we want to do is we want to change the slip so that it will be satisfied. So by increasing the slip, generally we're going to reduce the traction that are applied to the fault, and so we want to bring the tractions down so that they are consistent with the fault constitutive model. And the way we estimate the way we update the slip to try and satisfy the traction condition for the fault constitutive model is we extract a subset of the system associated with the fault. That's this equation 10. So we have a subset of our stiffness matrix. So we have the positive side of the fault, the negative side of the fault. Then we have our these L terms, these are the pieces of that C and C transpose that we've written out before. We have displacements on the positive and negative side of the fault. We have our Lagrange multipliers, and then we have our external force terms. And what we do is we perturb the Lagrange multipliers to satisfy the friction criterion. So we basically want to figure out how much we need. We know how much we need to change the Lagrange multipliers to satisfy the friction. So that gives us equations 11 and 12 that for a given change in the traction perturbation, that's this partial LP term, we want to compute the change in the displacements here on the left. And so this is another linear system, but it's much smaller than the linear system for the entire problem. And so we form this linear system and solve it, and then by taking the difference between these change in displacements on the positive and negative side of the fault, we can compute our change in the displacement field. And so this gives us, if nothing else of the system moves or if everything is constrained, then this will give us an update that actually tells us exactly how much slip is needed to satisfy the fault constitutive model. But in general, what happens is the rest of the model is not constrained, and so as we update the slip, the rest of the model, we could call it, relaxes and adjusts to accommodate that slip. And so we have to iterate and keep updating our slip estimate until we converge. If the fault is small compared to the entire volume and it's sort of in the middle of our volume, then it doesn't take that many iterations to update and converge. If we have a through-going fault in, for example, a 2D problem, say a subduction zone where you're having creep that goes all the way down to the bottom of the model, and your slip is going all the way to the surface, then now even a small perturbation in slip is going to affect the displacements everywhere in the volume significantly. And so it's in those cases where we have to where it takes much longer to update, because this approximation of what the slip is required to satisfy the fault constitutive problem is not as good as what it would be if we had just a small portion of the fault slipping. In the long term, we hope to improve the solver so that we can sort of more, instead of having these sort of inner solves and outer solves where the inner solve is just this portion related to the fault and the fault constitutive model and updating the slip, we hope to formulate a sort of more general constrained system so that when we update the entire solution according to the Lagrange constraints on Lagrange multiplier, we actually update the entire sort of search direction. So hopefully in those cases we'll end up with a faster convergence. But for right now, this works quite well when we have slip confined to just a small section of the fault in the middle of the model. Some words about the friction and the nonlinear solver parameters. The solver tolerances are very important. I think that's the biggest issue we find users running into, is that when they have problems with friction, it's their tolerances that are off. We'll go through the tolerances when we run some examples. So here's some basic rule of thumbs. So in addition to the nonlinear and linear solver tolerances, that's the KSP Krylov subspace solver, and the SNES, that's the nonlinear solver tolerances, the faults has a zero tolerance parameter. And this is because we're using an iterative solution, we're always going to have, for our slip estimates, we're going to have things like 10 to the minus 15 meters of slip. We're actually using non-dimensionalized units within Pilot. But it's usually on the order of something like 10 to the minus 15. We have round-off errors. And so we want to be able to say, is the fault locked or not when we apply the fault constitutive model. And so we have to use this zero tolerance. And so when we have these relative displacements across the fault, we compare them to our zero tolerance. And if they're smaller than our zero tolerance, then we assume the fault is locked and we set the slip to zero. If it's greater than the zero tolerance, then we recognize that the fault is slipping. So we want to make sure that when we set up our solver, that we take into account what our tolerances are for our linear and nonlinear solver are relative to this zero tolerance. And so what we want to do is we want our linear solver that's sort of updating at every iteration. We want that to have a tighter tolerance than the fault zero tolerance. So what we do to enforce that is our zero tolerance for the fault is essentially an absolute tolerance in non-dimensional space. And so what we do is we set the relative tolerance in the linear solver, that's KSP RTOL, to a very small value to force the absolute tolerance to be the convergence tolerance. And so we'll set the relative tolerance to something like 10 to the minus 20, our zero tolerance to maybe 10 to the minus 10 or 10 to the minus 12, and then we'll set our KSP absolute tolerance to be usually about 1, sometimes 2 orders of magnitude smaller than zero tolerance. Now our nonlinear solver tolerance, we want it to be just a little bit bigger than the zero tolerance so that we actually will converge in a nonlinear solution. Again, we want to deal with absolute tolerances, not relative tolerances. And so we'll set the SNES relative tolerance to be a very small value, 10 to the minus 20, just like our KSP relative tolerance. And then we'll set our SNES absolute tolerance to be 1 to 2 orders of magnitude larger than zero tolerance. And, our solver tolerances in general are, a function of what we think the resolution of our model. And so, if we're just doing a very coarse model, then we can bump these up by a couple orders of magnitude. If we have a sort of very tightly constrained solution, or we want to look at very small scale effects, then you're down around the 10 to the minus 10, 10 to the minus 12. So this is what our parameters, this is basically a summary of parameters within the fault constitutive model. And so in addition to our usual parameters of things like setting the friction model and so forth, in terms of the solver aspects of it, we need to be aware of our zero tolerance. So here I've set my zero tolerance to 10 to the minus 11. So I've set my relative tolerance to a very small value, 10 to the minus 20. My absolute tolerance to 10 to the minus 12, so it's smaller than my zero tolerance. And then my SNES absolute tolerance is 1 order of magnitude greater than my zero tolerance. Also within our that friction inner solve, that gives us an additional linear system where we can improve or optimize the solver parameters. And so, if you look in our 3D Haxade examples, you see that we're setting a friction PC type to additive Schwartz, and then the friction sub PC factor shift type to non-zero. So these are our general additive Schwartz parameters that we're now applying to that friction inner solve rather than just using the default PETC values. And we'll look at this in more detail when we look at do a hands-on example. Now our fault constitutive models, pilot contains some of the more popular fault constitutive models. We have static friction that has just a constant coefficient of friction. We have slip weakening, where the friction decreases with slip to a lower limit. Basically, it goes from a static value to a dynamic value over some slip sliding distance. We have time weakening, which is used in some dynamic simulations when you really want to just control how fast that slip weakening occurs. You basically replace the slip with a time dependence. So the friction decreases from the static value to the dynamic value as sliding occurs over some time duration. And then we have rate and state friction. We've implemented the Dietrich-Karuna rate, state, and friction with the aging law. And there are a couple other variations of slip and time weakening that we use when we run some specific SCEC dynamic rupture benchmarks that required a specific form of slip and time weakening. And they use this combination to try and help control the nucleation and force the nucleation in a specific way. So static friction, coefficient of friction is equal to a static value. Slip continues once a threshold shear traction is reached. You won't get stick-slip behavior because for stick-slip behavior, you actually need the fault to weaken. Because in this case, generally you only see a static friction parameter or the static friction model being used in a static simulation, not a quasi-static simulation, because the fault will never lock up to get the stick-slip behavior if you use static friction. And we'll see that in our example. A more popular friction model is slip weakening friction model. Here we're decreasing from a dynamic coefficient of friction to a static coefficient of friction as the slip progresses. So here shown down in the plot, we're going from a static coefficient of friction of 0.6 to a dynamic coefficient of friction of 0.1 as slip once slip hits a value of D0, then this coefficient of friction has reached the dynamic value. And in many cases, this D0 is usually on the order of a few tens of centimeters in most dynamic rupture cases. In some quasi-static cases, you could have it being slightly smaller. Time weakening friction looks a lot like slip weakening friction, only now here we've replaced, instead of a slip over a nominal slip value, we have time over some non-dimensional time constant T0. So instead of the coefficient of friction decreasing linearly with slip, now it's decreasing linearly with time. The rate and state friction model, this is the coefficient of friction. This is coming empirically from laboratory experiments. There's also some relation to creep models that can be developed analytically. The coefficient of friction has some nominal value, and then there's the direct dependence, which is A times the natural log of V over some nominal slip rate. And then there's the indirect effect, which is B, which is the log of V0, theta being a state variable that has units of time, over L, which is also known as D sub C, or a critical slip distance. We have chosen to regularize things at very small slip rates using a slightly different approach than what has been developed in the literature in most cases. Because we're using an iterative solver, we never end up with values of slip rates and slip of 0. So what we do is, instead of having sort of the coefficient of friction going to 0 using a hyperbolic function, what we do is once the slip rate hits some nominal, what we call a linear value, then we put in a linear dependence on the slip rate. So here in log space, it looks flat, but essentially we're going from a logarithmic dependence on slip rate at these higher values down to a linear dependence, which is looks flat here in this particular range of slip rates. Whereas if you kept that nonlinear value, or logarithmic dependence, you'd have this light-colored value down here. And so this is our regularization is adding this term over here. Generally, we set V linear to be just a couple orders of magnitude over our zero tolerance. So this helps stabilize and regularize the friction right down at the very smallest slip rates and very smallest slip amounts. So usually, you see it down here at 10 to the minus 11, 10 to the minus 12 slip rates. Equation 18 is the aging law for how the state variable theta varies in time. So it has this very simple d theta dt equals 1 minus the slip rate times the state variable over the length scale, or d sub c. The overview of the principal components for a spontaneous rupture simulation, we use the fault cohesive DIN object. That's DIN for dynamic, rather than our fault cohesive kinematic object. So whenever we use fault cohesive dynamic, that's the fault object for spontaneous rupture. We need our friction model, so we'll have a friction model component. In many cases, we're going to, particularly in dynamic cases, we will specify what the tractions are on the fault surface. So we're prescribing the tractions, and so we use a traction perturbation object. And this provides the same spatial and temporal variation of the tractions as we use for our time-dependent boundary conditions. So it has the same type of form in terms of the time dependence and spatial dependence, and uses the same spatial databases. So we can put in an initial value, then we can put in a spatial variation with a temporal variation, and we'll look at that when we run one of our problems. And then, of course, we need our nonlinear solver because with the for quasi-static simulations, we need the nonlinear solver because we have this feedback between the fault constitutive model and the slip. In dynamic simulations with the explicit time stepping, our left-hand side is the mass matrix, which is diagonalized. And so we no longer have a nonlinear dependence on our solution with the fault constitutive model. And so in that case, we use just a simple Newton-Raphson updating of our slip and slip rate to make sure they're consistent with the friction model. But our traction perturbation, we don't need this extra linear solve. It's able to still use the nonlinear, not the nonlinear, but the trivial solver in our explicit time stepping scheme. So here we have the examples of our spontaneous rupture parameters in a .cfg file. So first, we set the type of fault to a fault cohesive dynamic object. We're going to set the type of friction that we have. We give it a label for which particular type of friction we want on a particular fault. Then we give it our properties for the friction model. So in this case, we're just going to use a uniform database. We're setting our, because we have static friction, we have our coefficient of friction and our cohesion. We're going to use a static coefficient of friction of 0.6, a cohesion of 0 megapascals. Then we have our traction perturbation. We're just going to use an initial traction perturbation. In this case, we'll use a spatial, one of our simple spatial databases. We give it our label for that spatial database so that that's included in error messages, and then the file name. So